Okay, today I've had a couple of questions about the first two problems on the homework about high frequency and reduced order models. We covered them briefly in lecture and then in lab before break, but I wanted to go back and revisit that a little bit because I think we didn't do it quite justice when we looked at it first time. So the topic is high frequency in our systems that we are not modeling in our analysis. And this is common. I mean, as engineers, we do this all the time. True physical systems are much, much more complex than we model them in our analysis. And so the question becomes, when can we neglect them, or these high frequency phenomena, and when should we include them? And so we're going to tackle that over the next couple of short lectures and see if we can't make some sense of that. Before we move on with that, I want to just give an example. I think I showed this in class before break, but this is a typical example of how this might come about. Here we've got a drivetrain, electric motor driving this gear train, and this actually could be modeled very similar to what we model in the motor lab. We've got a driving motor, and we've got some inertia, we've got some friction, and then we've got an output, either a velocity, an angular velocity, or an angular position. And the only difference between this and our motor lab is that there's a factor in there, a gear ratio in there that we would include in our model. But we could model this exactly like we do in our system. Now, that would work really well, except for when we start trying to drive this system very, very hard. When we start driving this system, some assumptions that we probably made at the beginning will start falling apart. We probably assumed that these shafts in here were rigid, okay, and did not flex. And so the position of the motor shaft in here was proportional to the position of the output shaft in here. Okay? Now, if we start driving this really hard, what we're going to see is some flexing of that shaft. We know from our mechanics of materials that if we apply a torque to that shaft, it's going to twist. And so we're going to get some these shafts starting acting like springs, and that's going to introduce a new set of poles for us in our model. So they will be high frequency poles, but nonetheless, they're going to show up. We also will start picking up some friction in here that we might not have accounted for, depending on whether these are bearings or bushings. We might pick up some additional friction at high speed. We might pick up some chatter associated with the dynamics of the roller bearings that would show up in our system. Also, some slop in the tolerance of the bearings would start showing up. The interfaces here between the gears would start showing up because the teeth would start to bend. The dynamics of the teeth meshing together would start to bend. Now, all these phenomena we consider pretty high frequency, and if we don't drive this hard, they are negligible. But should we include them, and when can we ignore them? That's the question that we're going to start dealing with in here. So we'll see that in the next lecture.